Welcome to the lecture Recurrent Neural Network Part 2. In this lecture, we are going to understand the training of recurrent neural network using backpropagation through time algorithm. Then we will discuss character level modeling through RNN as through an example, and then we discuss different deep RNN models. Today we'll start how a RNN is being trained, and the algorithm which is used to train a recurrent neural network is called backpropagation through time. Now, backpropagation through time essentially a backpropagation algorithm that can handle the sequence and time dependencies, and we'll see how actually it do or it train this RNN. So as we have discussed earlier that the RNN, when we unroll or unfold in time, it looks like this structure. You can see every RNN node there is an input. It maybe may not be, but just for our very simplistic understanding, said these are the inputs, and these are weights, and you can see the weights are same. That means the weights sharing is used. After that, there is a RNN node S1, S2, S3, S4. Now, what is this 1, 2, 3, 4? These are the time instances. The first time instance, the second time instance, third, fourth. So we have taken example for only 4 time instances, just for our understanding. Now, hypothetical, this is a typical hypothetical example where this kind of RNN is unrolled and we assume that there is only 4 time instances. So, and for this purpose, this x1, x2, x3, x4 are 4 inputs, and these are weights wx, and for there is some state variable from the previous state. Since h0 is basically there is no previous state, it is initialized something, and then this h1 is coming from this s1, it is going to feed s2 and so on, h2 to s3 and s3 to s4 and so on. So that we know from how this h1 is being formed by show of this is wx into x1 plus wh into h0 and so on, that plus, and that will get, and we put some non-linearity over there, maybe tan h, we get h1. Now here when we get h1, then we can use this another weight matrix, that is wo, that to get the o1. So these are the more or less that we have discussed in very details in the previous lecture. Now we are discussing that after this unroll or unfolding in time, we use the standard backpropagation on this unrolled network. Now here one thing is interesting here, since sequence length here is t, that means here t is equal to 4, then the RNN becomes a deep network with t layers. This is a kind of analogy. And you see there is a 4 time instance or t time instance, and it is a t layer or 4 layer network, and 1 layer per time step. It's just there's a deep neural network or a kind of CNN type of network, but their nodes are in a different time steps. And for that we said that this particular example what we have taken, this has 4 nodes, that means this, and with shared weights. So this is the basic, very basic or naive structure, or a very hypothetical example of RNN, and we use the standard backpropagation over it, and we'll say This is backpropagation through time. And let's see how actually this works. Now, what we have said that this is our network, and with 4 nodes, shared weights. Now we use softmax here. This is just assumptions with this for this output as output function. And what is important, what is the loss incurred? Now, as we know that when we generate output, we generally not getting what exactly we want. Specifically for the initial epochs, we get whatever we get, it is not very close even to the actual or targeted output. So there is a loss. And according to the loss, what we will do? We calculate the error gradient, and based on this error gradient, we update the weights in normal backpropagation. Here also we have to understand what is the loss function is associated with these nodes. Now, as we can see here, that in this RNN of 4 nodes, there is a losses at each time instance. So this time in H1, this L1 is loss, S2, L2 is loss, S3, L3 loss, and S4, L4 is loss. And as we have said, we have used cross entropy as the loss function. Once this, and the basic thing is that the total loss. So this loss is L1, L2, L3, L4 is this node specific or time instance specific, and there is a total loss. If T is the total number of time instances, then this loss is basically sum it over I is equal to it is equal to 1 to capital T. Capital T is total number of time instances. That we can get this. So there is a conceptually there is a two kind of loss. One is the individual loss at the different time instances, and is the total loss, that is addition or some summation of these losses here. That is important to understand here. Now, can see what actually we want to do. In general, what we understand about a training procedure or training algorithm, we essentially have to know these weights parameters at Wx, Wh and Wo. Based on our supervised concept, there is some input and outputs are already given, and based on this we get some values or predict some values, and we get the losses, and based on these losses we calculate the error gradient, and this error gradient is going to use to update the weights at the different layers. It was discussed in normal backpropagation. Here more or less same, only difference is that backpropagation are working in a time direction. So with this time, every time instance is one layer. So if you say this L4 kind of thing, it is propagating to S4, S3, S2, S1. In CNN kind of thing, these were the layers, these were the layers. Here it is a different time instant. That is basic difference. So that's why we say backpropagation through time. So as we have seen the last slide, we calculate the total loss. And what is our problem statement at this moment? That we have to understand, or we have to determine what are the Wx, Wh, Wo using this kind of PPTT algorithm, so that our intended this x1 to y or o1 or X to O mapping can be fulfilled, or we can get a idea or get a model that map this X input to output as per our intention. Now, first of all, we try to understand what is W. W is basically the weight parameter for output layer, and for this backpropagation, we have to calculate gradient. So, first of all, we have to find out what is the error gradient with respect to this WO. So, D of L. So, now here L is the whole total loss, but we can here easily we can get this in this way. Here del of L of del of WO is equal to, just to sum it up, for 1 to T, where T is equal to 4, of D of L4 of D of W0 plus D of L3 of D of L4 and so on. So that is very straightforward. We can easily do it. And if we get it, we can update this weight accordingly as per simple backpropagation rules. Okay. Now comes that what is the error gradient with respect to WH. Now here WH, you can see these WH are somewhat connected through this time axis or time channels. So what that makes the difference from the normal backpropagation here, this H4, H3, H2, H1, H2, this basically these functions and the corresponding the weights are somewhat connected. Okay. So here we can see here that again, if you see here, we can find out this del of L of del of WH is equal to 1 to T del of LT del of WH. This is also not very complicated or easy to understand, because that if we can find out this del of LT of del of W of H, that means this W at this hidden layer, so we can very easily get the total loss. Okay. Now this, how we get this W of L, W of H by W of H and del L del WH. So you can see that first then we have to get that this can be obtained the summing gradient and all the paths to that we can. Now take this one, that how we find del L4 del WH, because if we find L4, we can get L3, L2, L1 and so on. So what is L4? L4 is the difference of our predicted output and this is the target output. Okay, this is our predicted output. This is our target output. This is a constant, so that's not a big issue. So if we, what we have to get this del L4 del WH. Okay. So using this chain rule, we can write that del L4 del H4 and del H4 by del WH. Now the major things is coming here. Now this H4, you can see this is a kind of a state variable that is going to the next state. This H4 again makes an H3 depends, H2 depends, H1 and H1 so on. So this thing we have to think, what del of H4 by del of WH. Let's start our next understanding from here. If we can find out that this value, then other things are very straightforward, nothing complication in it. Okay. Now coming here, so our problem is that we have to understand del H4 by del of WH. Okay, so we started from here. Now, essentially, what is the relations of this? This is also again very straightforward. That is H4 is basically tan H of WH3 plus WB, and plus there is another term. It is this term Wx into X4, but at this moment, because this is, since we are going to differentiate with WH, this is a constant, so it doesn't make much sense here. Now here one thing is very interesting. Now when we take this derivative of this, now this formation is a kind of ordered network, and when we do this kind of derivation, there is a two part. One is we considering all are constant, and another we considering it how H4 is depends on H3, H3 depends on H2 and H1. So essentially when we are differentiating, by the virtue of the differentiating a paired network or the formation, it is that it is dH4 del H4 del of H plus del of H4 and this. Now if we, that particular thing is important to understand, and that you have to remember. Okay, then things has become very easy. Then what we are basically doing, we put in this DH, we expand this as of this. So rest thing are same, only we put DH3 plus the same as of DH4 DWH, we just put it 3 here, and now it is coming from 2, so it is 2. So DH3 by DD of WH plus del of H3 del of H2, H2 del of WH. Now again, what these things there, we expand del of H2 del of WH in this way. So del of H2 del of WH plus del of H2 del of H1 del of, okay, and then if we sum it, just basically do this multiplication, come up with this equation. And if you do some simple algebraic manipulation, we can find that this is formation DH4 the DH del of H4 by the WH, del of H4 del of H3 del of H3 by del of WH, and this is the, basically you can see that this is a symmetrical kind of expression, and this is del of H4 and this is I, so H4 H3 H2 H1, so it is summing up, so that's why I, and this is H4 H3 H2 H1, so del of HI del of H. So it basically, if we sum it up, we can get this. Okay, so this W, this del of H4 del of WH is essentially this. Now what is this? We have to put this to that 2 here, because del of L4 WH to del of L4 del of H4 into this. So we put this here. So that del of L4 initially was this del of L4 by del of H4 of H4 del of WH. Putting the value of this, what we get here? Here we get, this is the value of del of H4 del of WH. So del of this value, actually we put this value, we put it here. So we can get here what is del of L4 del of WH is equal to del of L4 by del of H4 summation this 1 to 4 del of H4 del of HI del of HI del of WH. So now this 4, if you put it T, because from generic terms, okay, then it become del of H L of T del of WH, del of LT, T is equal to 1 to T. So this, you can put it here, capital T also, it's not an issue. So this is for T time instance. So in this way we can find that this W of L of T, W of T. And when if you find this of W of LT, we can easily go to that 1 T is equal to 1, T is equal to 2, T is equal to 3, T is equal to 4, and so on. So we can get it. So in a similar way, that this Wx also can be formed, okay, because it is also coming through this, So in a way, error gradient with respect to Wx can be computed in this. So del of LT, del of HT, and only difference is there is the WH, Wx. That's it. Okay. So what we have seen, that the problem was I have to find this Wx, Wh, and Wo, and using this BPTT algorithm we can find these weight parameters as this W of LTW. So this is the basic error gradient, and 41 to capital T, and then capital T is number of time instances. And if we get this, we can easily update weights parameter this using BPT, or we can use any kind of optimization algorithms like gradient descent to get this weight update done. So in this way we can use BPTT to train our RNN. Now what is important to understand, that what is the major issues with this backpropagation to time or BPTT algorithms. Now as we see that if we extend our network, initially it was hypothetically, we take an example that it was only 4 time instances or 4 node in R. Now here we extend for a 15, maybe is extend for a 30, 50, even 100 and more than this. Now if there is a bigger network, that means it is going to handle a very big sentences in natural language processing, or a very large video sequence in image or computer vision problem. Then this BPTT algorithm is not that much useful because of vanishing gradient problem. As we have seen the similar thing in case of our CNN also. If the network depth is very high, then the vanishing gradient problem arises, and the issue is the initial layers is not that much properly converges because of the error gradient become decaying when it reaches the final to initial layers. So that was the vanishing gradient, what we have discussed very in detail. Now this is the vanishing gradient problem. Another kind of linked problem, or is a related problem, you can say, since the longer sequence required this kind of, or longer sentence forward, easy to understand. Then if this is a longer sentence, this kind of structure, due to this vanishing gradient problem, cannot model this longer sentence properly. So if there is a word here and word here, this is called long range dependency. Okay, so that cannot be properly modeled. That we'll see later how this problem is being solved. Okay, but at this moment there is some sort of way out of this. So that is called truncated backpropagation. As you see here that there is a long sequence. So why not we break this long sequence in some subsequences? Now you can see here it was initially the 15 sequence and the first 5 nodes or 5 time instant are taken here, and we use this backpropagation here. Okay, now in this backpropagation algorithm, since number of states, or you can say this time instances, is much lower, then it relatively work better. Okay, so this thing is run forward and backward for chunks of sentence or subsentence of subsequence instead of the whole sequence. And this approach is a very straightforward approach, and this approach is called truncated because we can sum up. When it is being trained, then we go to the next. Now this we are not touching it out, it is since it's been done. So here also we can see that how this the similar thing can be achieved. The only difference is that the number of sequence or number of states is less. Next state is 10, this 15 last 5 sequences, and if we do it by breaking the sequence in smaller subsequences, then the backpropagation algorithm works or performs relatively better, and by this we can achieve much better performance or much better convergence. Okay, now we are going to understand how this RNN structure or RNN architecture can be used to implement some NLP or other vision task. So we start with a NLP thing. Now here we introduce one model, is called encoder decoder model. In this encoder decoder model, that is two part, and we can say there is two RNN is involved. One is encoder RNN and other is decoder RNN. This encoder RNN essentially is many to one model, and decoder model is one to many model. As we can see here in our encoder module, there is a t time instances. So there is a t number of nodes in the RNN, and as usual there is a t different inputs. If you consider it is a sentence, let's say English sentence, then there is a t different, capital T different words in sentence. And as usual, as our initial understanding, these input weights are shared, and these WE are basically this hidden state weight parameters. We put E as per encoder, and this has been also been shared. So this X1 is given to this H1. So this H1 is going to produce H1. That is in our traditional or as usual formation, that H1 is equal to some nonlinearity, let's say tan H of Wx into x1 plus We into H0, and we put nonlinearity over that and get H1, and so on. In this thing we are basically going to do. So H1 to S2, from S2 produce H2, that is come S3, and so on. So this is the encoder side. Now, similar, it's a decoder side. But before to discuss decoder, one thing is very interesting here. What is the final output of the encoder? So this is basically HT, that is the final output. The output or this hidden state output coming from the final state of the network. And what it is called, more technically we called it context, but apart from that, I can say this is kind of some abstract of this sentence. So as we can, for our understanding, we think this is basically an abstract of this the whole sentence, and it is here, and it is being prepared by this encoder arrangement. Now this is going to the input, the state input of this decoder. And decoder also has the required number of steps or time instances as per the requirement or as per the application. And then this H1 is here, that is produce H1, H2 is produce H2, so on. And what is H1? H1 is now basically coming from this HT to WT. Since there is no X1 or something input as a whole, as a time being, maybe something, but for this very simplistic understanding, there is no input is involved here. Now, whatever is our H1, that is if multiplied with WO, we can get 1. This H2 multiplied with WO, and so on. So this whole formation is basically a encoder decoder model that actually, given a sentence, let's say in a particular language, it can convert this or translate this sentence to another language. Say if it's a English, it may be a German, or maybe a Spanish, it will be Italian, or something like that. So here, this is the very simplistic approach. Now, this kind of thing is a very naive NLP task. Okay, let's try to understand. This is even more simplistic task. It's called character level modeling. So now there is one word, and we have to find out that what are the words. Now you can see this word. Let's say the word is catch. As a training sequence, we have a catch word. Now in this catch word, how many different letters? C, A, T, and H. These 4 letters are there, or characters are there, and this basically constitute the vocabulary. So these 4 words. Now for these 4 letters, not word, or 4 letters or characters, we have to some sort of representation we required. It is called the embedding. So it's character level embedding. For every character, we have this representation, and it is a very simplistic representation. It's called one-hot encoding. So that C, say 0001, A 0010, T 0100, H 1000, and something like that. It's a very easy to understand. Okay, now it is our one state or of one time instance of ARN, and you can see the XT is coming in WX, it's coming as T. The previous input state is coming and is through WH, and HT is produced, and we can get the WT. How we can HT? That is tan H is our activation function or nonlinearity we are putting, and before that we WH into HT so on plus WX into XT, and this summation put in nonlinearity we get HT, and YTW HT. So this is a simple structure. Okay, now let's try to understand how this model is being trained. Okay, now first thing is that these input characters C, A, T, C something. Now this is catch C, A, T, C something like C, A, T, C and so on. So C means what? 0, 0, 0, 1. So 0, 0, 0, 1. What is for A? 0, 0, 1, 0. What is for T? 0, 1, 0, 0. What is for C? 0, 0, 0, 1. And so, so this is the input layer. This formulate the input layers. And then it is coming the hidden layer. Where hidden layer? The previous layer input is coming as state input. This WHT minus 1. Now WH is going to multiplied with this. And WX is this. XT is this. What is multiplied with WX? We get this. So WH to HT minus 1 plus WX. And we put a tan H nonlinearity over there. Get HT. So here we can get this. Next, the output layer. Now here is the main catch. This is the input. So input character is this. What will be the target output? So how actually this model learns? So what is the target of the next word? Given that is C, what will be the next character? Okay, see, so next character should be A. So target output is A. Fine. Since it is a supervised paradigm, so C and this should be. And you can see the target output is somewhat like this 2.5. So because it is A is what 0, 0, 1, 0, so it is. So it may not be that. Just for understanding, I put easily. Okay. Now second, it is A. Now this is the input here. The next input is A. What will be the target output? After C and A, this is T. So T is the target output. Now again CAT. So this T is basically. And what will be the target output? Then C here. So this is the target output. And so on. Now after C again H. So it is coming. So basically this catch word is trained in this way. That is very important to understand how, what is the input sequence and what is the target output. Okay. So this is the training phase of this RNN. Now in testing phase we have a similar architecture. Now here you can see that this input character is C when this is the input 1 encoding. Now as our normal hidden layer is there, that means the hidden layer is coming, it's RNN state. Now this is our output, and if output put the softmax, we got this sample. Now this is C. So next predicted word is, since it is a word is catch, is A. Now this A is coming where? Here. Because as we have seen before that there is no input as such here. So this is the it's coming because it's the next letter to be generated. After C, A come. So what is now? It is our intention. After C and A, what will be the output? Or what is the character? A similar thing will come, and the target output is T. Okay. Now this target output again coming into next. And in this way it is going. So one important thing, it is very important to understand here, that this output of the first time instance is going to be the input to the next time instance. some kind of auto regulation or is there, but we'll discuss this in later. But this is kind of, so this is basically going to this. So this t will come to the next, this will come to the next, and this. So you can see, you can go to C A T C H. So this is the catch. So this is the way this the character level RNA at the training time going to sorry testing time we're going to use. Okay. Next, what we'll see that here in this particular that we use the 1-hot encoding that we have done. So different encoding. So in this way, what we have, this character level embedding or character level modeling can be done using this encoder decoder kind. Now another important thing is what are the different RNA models that have been used but more in deeper. So this is our known thing, and if we put it here we can get some next. So this is just for hypothetical understanding. So deeper RNN model can be used. Another important thing is called bidirectional RNN. In this bidirectional RNN, that it is our forward direction. Similarly, another level of put over it is called indirect backward direction. So it is helpful because that recurrent neural network that process in both direction, forward and backward. So it can use the past and future context at every time step. As you can see, this YT is coming from ST from the both sides. This coming from this backward side as well. So this kind of context, we want to bank to deposit money. What bank depends on the what comes after it. So in this kind of sequence, bidirectional is very much helpful. Okay. So in summary, what we have discussed in this lecture is training of RNN. We discuss BPTT, backpropagation through time, then character level modeling through RNN example, and some deeper models. In next, we start LSTM. Thank you very much.